So in this video then, I'm going to be looking at just a couple of questions based on mass spectrometry. Now, these are just going to be mass spectrum questions, so I'm not going to be including any other analytical techniques here, because some questions, of course, in the AS course and at A level will just be focused on one method and not a combination. So it's a very good idea to be proficient at doing all of them individually, because sometimes you will be asked to do them separately with no other information to help you. So quick reminder then, mass spectrum, the key parts, okay, so the largest peak is called the base peak, represents the most common fragment, and you can also work out the molar mass of your product or whatever it is you're looking at by looking for the molecular ion peak. Now this is the largest peak furthest to the right. So let's have a look at what we've got here. So it says that alcohol A this is a mass spectrum. Determine the structure of alcohol A and fragment ion X. So it's only 3 marks, so it can't be that complicated. So it must be something fairly straightforward. Now, the molecular ion peak is this peak here at 60. Okay, yes, there is, if I just erase that circle, there is a tiny little peak after 60 or 61. This is not the molecular ion peak. This peak arises because of isotopes. You know, if you've got the odd carbon 13 in there, you'll have a mass of 661 instead of 60. So 60 is the biggest peak furthest to the right. So therefore, the MR is 60. So it's an alcohol with a molar mass of 60. Now, we know what alcohols are. Alcohols contain OH groups, so we know that something there is an OH group. And we know it's going to be bonded to a carbon. Okay, that much is certain. So if we look at 60, yeah, if we subtract 17, which is the alcohol group, we end up at 43, which is actually a fairly big peak. So again, this actually gives us credibility. If we go from 60 to the next peak, we get, minus 17. That's the OH group. Okay, that's the minusing the OH group. Because remember, fragments are what you get when you take the molecule and split one of the bonds, and you look at how big the piece is left. You might be wondering, what's the peak at 59? Well, imagine, for example, I do have my alcohol. We don't know what the alcohol is yet, but we've got a good idea. If we just take the alcohol group, it's an O to a H bond. If I break the O to H bond, I'm losing 1. And that's why you've got we've got a slightly larger peak at 59. That's the loss of hydrogen. Counting back from 60 to 43, that's the loss of both hydrogen and the oxygen, to leave you with just the remainder of the group. And the remainder is 43. So then you've got to think, well, 43, how many carbons are going to be in my chain? Well, if there's 43 remaining, it can only be 3. Okay, 3 12s are 36. Okay, 4 12s are 48. So it can't be 4 carbons. That would be too many, and the mass is wrong. So must be 3 carbons. Let's just put them all in the chain. And the best part is you can't branch 3 carbons. So they have to be in a straight chain. And looking at this, it's an alcohol. If I just add hydrogens in here, do I get the correct amount of numbers? We'll see. So I needed 43. I've got 12, 24, 36. And I've got, what is it? 1, 2, 3, 4, 5, 6, 7 hydrogens. So 36 plus 7 is 43. So the structure is propanol. Okay, propan-1-ol. Doesn't have to be propan-1-ol though, because it could be propan-2-ol. Okay, we know what the structure looks like, but how do I know the alcohol group isn't somewhere in the middle? Well, this fragment X is likely going to give us all the clues that we require, because X is at 31. So I need a fragment that is going to give me 31 in weight. So can I get a fragment at 31? So looking at my diagram then, if I take, this carbon, this CH3 group is 15, this CH2 is 14, so that's 29. What about the other side? If I've got CH2 is 14, plus oxygen is 30 and hydrogen is 31. If I break this bond, the fragment on the right hand side equals 31, which matches exactly with the base peak in my spectrum. Okay, so if you want to draw this bit out, it's nice and straightforward. Okay, we just draw it out and make sure when you've got a mass spectrum, of course, you don't have a bond on this carbon, so it is positively charged. All fragments must be positively charged, otherwise you haven't drawn a correct fragment. So there you go, nice and straightforward there. Okay, the alcohol was very easy to get, and the fragment peak matches up exactly with what we expected to see. Okay, we looked for 31. It's the most common fragment because we're splitting the compound straight down the middle. Okay, and you get this CH2OH fragment, and the MR is 60. So again, you don't have to count back and find all the little peaks, you know, in your working out, but it does help justify sometimes where these fragments have come from. Okay, so if you've got this, you know, this little drawing, obviously you can just then count up the different sides of it and see which ones fit. If they don't fit your spectrum, it's likely you've got the wrong, you know, structural isomer, which can happen every so often. Right. Next little question then. So this is just a bit of a straightforward thing, okay? There's nothing too complicated here, but it just highlights what sort of questions you would get asked, okay? So mass spectrum questions aren't always figure out what the identity is. Sometimes it'll tell you it's 1-iodopentane. Question is now, what information is given by the peak labeled X, so the furthest to the right, but not the final peak, so the biggest peak furthest to the right. It's the molar mass, the molecular ion peak. So you can just write molar mass or molecular, you know, molar mass, okay? Okay, it's the molecular ion peak. Nice and straightforward. And then it says write the formulae of the ions responsible for peaks level Y and Z, and it tells you what the MZ is. You haven't got to look it up. So one's got 71 and one's got 43. So 1-iodopentane. Okay, if you draw it out, one, and you've got 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon. Okay, you've got 1-iodopentane, and everything else is a hydrogen. This becomes quite the easy task at this point because you need to look at the fragment bit. So let's have a look. So 71 and 43. Now immediately we can actually figure this out. We can actually figure this out very, very quickly because we're looking at the fragment peaks. So we're looking at we need something in this compound that gives us a molar mass of 71 in total. Now iodine's molar mass is bigger than 71. So we're probably breaking off the iodine, okay, at least. So the question then becomes just how many of these carbons add up to give 71. So let's say I've got 1, 2, 3, 4, I've got 5 in a row, that equals 60. Well, I've got 11 hydrogens, so that's 71. So for 71, we're clearly breaking the bond here, and the ion is going to be CH3, CH2, 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 CH2 plus, and that's it. Okay, that equals 71. And the second one, MZ43, once again, can't contain iodine. Iodine's too heavy. It's just going to be some of these carbons. So let's just count up. So the methyl group at the end, 12, 13, 14, 15. I've got 15 here. The CH2 is 14. That equals 29. And I've got another 14 here, which gives me 43. So that means I'm just breaking my bond here. And everything on the left-hand side is the fragment ion I need. So once again, structural formulae, just write it along, CH3, CH2, CH2, with a positive charge. Okay, don't forget the positive charge. It's massively important for mass spectrum fragment ions. And that's it. That's all you need to put down. Okay, You can work out very quickly based on the numbers, there's no iodine present, and then it just becomes a case of counting along the carbon chain, how many do you need to go down before you get to the number you want. So, last little question I'll do on this then. So 2-iodo 2-methylbutane is an isomer, so draw the structure of that, so this isn't too complicated. So methylbutane, so butane's along this chain, so 1, 2, 3, 4. 2-methyl means you've got a CH3 here. You'll also have iodine here, and then you'll have CH3, CH2, CH3. And then it asks you to predict one similarity and one difference between the mass spectra of the two. Well, in this instance, so we look for the similarities and differences, and straight away, the first similarity you should think of is, well, it's the same compound. It's the same thing. It's just an isomer. So that means that the MZ peak, the molecular ion peak, will still be where it was before. So it will still be at, what is the value? 198. So you'll still get a peak at 198. Okay, that will be the same. The difference will now come with the fragments, because remember earlier when we looked at this, it's actually the one I've still got drawn. Remember earlier we had a peak at MZ 43 and one at 71. Now the one at 71 will still be there, because if you break this bond here, everything else still equals 71. So that's the same. In fact, that could be your similarity if you wanted it to be. The peak at 71 is still the same. But what about the peak at 43? They haven't included this as a, just for no reason. They've included this because it's not going to be the same. Okay, it's a clue. Okay, to the next part of the question. To get a peak of 43, I need a CH3, a CH2, and a CH2 all next to each other. In my new compound, I can't have that. There is no bond I can break anywhere to give me 43. I would have to break 2 bonds, at least. Maybe 3 or 4. In fact, I'm not even sure it's possible if you break even more than 1 bond. Okay, there's no way I can get a CH3 and 2 CH2s next to each other to make 43. Mainly because I've only got 1 CH2 group. So the difference would be there is no peak at MZ43, because the fragment ion that I'm looking for is no longer there. So there's a few little questions based on mass spectrometry. Okay, they are very straightforward. Generally, it's just looking at a spectrum. Normally, it's looking at assigning fragment ions, or working out the structure of a very basic compound, because obviously mass spec on its own is not the most powerful tool to figure things out. But as long as you can describe what you're looking at, and you can confidently draw fragment ions and put positive charges on, you should have no trouble answering questions on mass spectrometry.